Dr. Chen-Ning Yang, a Nobel laureate in physics, is the Albert Einstein Professor Emeritus in Physics at Stony Brook University and the founding director of the C.N. Yang Institute for Theoretical Physics at Stony Brook. His good friend, Dr. James Harris Simons, is a renowned mathematician, investment advisor, and philanthropist. A former chair of the math department at Stony Brook, he heads Renaissance Technologies, an investment fund that trades billions of dollars in markets around the world. He and his wife Marilyn recently donated $60 million to Stony Brook to create the Simons Center for Geometry and Physics. And gentlemen, it's a great pleasure to be able to speak to both of you. I was quite comforted yesterday to learn that each of you at certain points in your relationship were unable to understand what the other one was talking about. I found that a very comforting situation. Now that physics and math are back together again, is everybody caught up with each other, Dr. Simons?
Well, I still, generally speaking, don't understand a heck of a lot of physics. So I don't know. I think a lot of mathematicians have certainly caught up to some extent. People who are interested in these particular areas, which do center around geometry to a large extent, have gotten more familiar with the physics lingo, at least, and what they're after in many respects. And I expect the same is true on the physics side.
How about Dr. Yang? Do you now understand what the mathematicians are talking about?
Mostly not. But let me explain. Math and physics, and in fact every discipline, has now become very big subjects of investigation. In contrast to 100 years ago, each covers now much broader territory than before. So when a mathematician talks to me, most of the time I cannot understand. But the amazing thing is that between what they talk about and what we talk about, there's a region of overlap. What is amazing is this region of overlap is very, very fundamental. And it's mostly related to the geometry part of mathematics. So although it is only a small fraction of both mathematics and physics, it occupies an essential position in both, sort of at the source of the lifeblood of each. And everybody expects, both mathematicians and physicists expect that this will continue, that the future developments of both disciplines are likely to be deeply entangled in this central region. And that is the reason why everybody is very happy that with Jim and Marilyn's generosity, Stony Brook will be able to launch into this central area of research for both disciplines.
I want to follow up on that, but I also want to mention that I heard you say at one point you wrote that there were two types of mathematics books. Tell me about that.
Yes, that was when in 1969 or thereabouts, I found some similarity between some mathematicians' formula and some formula that we physicists were talking about. So I went to Jim, who was department chairman of math at that time, and he instantly said, these are the same thing in fiber bundles. So I said, what's fiber bundles? So he gave me a book, a very famous book written by a Princeton mathematician named Steenrod. And I took the book back and got very frustrated after studying it for a couple of hours. So later I joked there are only two types of modern mathematics book. One you cannot read beyond the first page, and one you cannot read beyond the first sentence. And the Steenrod's was the latter kind. And the mathematicians agree that they think that this is an appropriate joke to a certain extent. But that does not mean that they would abandon that style. There is a certain rigidity, but there is certain advantage in this way of writing. So some of the mathematicians persist in writing that way.
Is that the way you would write, Dr. Simons? Are you rigid?
Steenrod's book was always not an easy read. Some people are better writers than others, and as time goes on, certain fields become clarified and then, as a result, easier to explain. So I never got very far in Steenrod's book either, and learned that material that's in that book in other ways. But Steenrod's book was written sometime earlier, well before I gave it to Frank. So it's like a lot of subjects. At first, they're very difficult to understand and therefore difficult to explain to other people because you don't perhaps fully understand all the ramifications yourself. Gradually, things become clearer, and things are easy to explain. So, you know, that's Steenrod's book. I think will always be a particular example of something that's pretty hard to read.
Is fiber bundle something you could explain fairly easily at this point?
I could if I had 10 minutes.
I see.
You want to give me 10 minutes?
I'll give you 10 minutes after this interview.
Fine.
You're funding the Simon Center for Geometry and Physics. What do you hope and expect will happen there? And what's the, to get back to something that Dr. Young said, what is the connection between geometry and physics that doesn't connect the rest of mathematics?
Well, obviously, most of mathematics is involved in physics. Calculus is involved in physics, and you have to know how to solve linear equations or whatever, so inverted matrix, all that stuff. Most basic mathematics, or a great deal of it, finds its way into physics and is necessary. The modern thrust of mathematics into geometry, which has occurred over the last, say, 75 to 100 years by now, has very much deepened a certain area of mathematics, which is generally called geometry. And those areas have become particularly relevant in physics. So, and physics has always had quite a bent towards the geometric side of mathematics. For example, if you look at the work of Archimedes, who was a great scientist, the more I've learned about him, the greater he seems. He did both mathematics and physics. I don't think completely separated the two in his mind. For example, he quickly learned how the importance of the center of mass. Now, he was only looking, at least initially, at the center of mass of a two-dimensional object, of a flat object, which you might think, well, doesn't even have any mass. But, of course, if it's a little thin plate of metal or something. So, geometrically, you find a nice formula for the center of mass. Well, you couldn't do physics without the notion of the center of mass. Elementary physics, that's the way you look at forces that are applied to the center of mass, and then the whole thing becomes simple. So, from the very beginning, at least back to Archimedes, geometry, the geometric side of mathematics and physics were quite intertwined. Newton himself did a lot of his work with geometric, stimulation and inspiration, and his writings involved a lot of geometry and depended on that quite a lot for the physical intuition. So there's nothing really new about a geometry and physics interaction, except how these very advanced areas of both subjects have become so intertwined in the past, say, 40 years. Yes.
Yeah. Let me supplement what Jim just said.
Please.
As you said, traditionally, physics and mathematics had deep relations, especially physics with geometry. And in the 19th century, Maxwell wrote down Maxwell's equations. That's the greatest piece of physics in the 19th century. And if you read what he wrote, he was thinking deeply geometrically. However, the person who explicitly stated that the physics has to be geometrized was Einstein. Einstein first did this in the beginning of the 20th century by geometrizing the concept of gravity. Gravity used to be thought of as something that two bodies would attract each other at a distance, and that's started from Newton's times. Einstein converted that into a geometrical theory, a completely geometrical theory, and that's called general relativity. That's one of his great achievements. More than that, after that, he then said that not only should gravity be geometrized, as I did, but other forces in nature should also be geometrized. What is meant by the other forces of nature at that time? It means electromagnetism, electric and magnetic forces. Magnetic forces used to be thought of, you have a charge here, you have a charge here, they repair each other if they have the same signs. Like Newton's gravity, action at a distance. And Einstein insisted that this kind of electromagnetic forces should also become geometrical. And that was the beginning of the idea of gauge theory, taken up by one of the great mathematicians of the 20th century, Hermann Weyl. And he introduced the idea of gauge theory, which developed through all these ages to today, and it has a profound influence on the re-emergence of a common interest between the geometers and the physicists.
In many ways, you two gentlemen represent this coming together of
I would say we contributed to the beginning of it.
Tell me about
Would you agree with that?
Yeah, I think we contributed to the beginning of it.
Tell me about that.
Well, from my point of view, when I came to Stony Brook, Frank was good enough to tell me some of the things that he was doing, and since I knew so little physics, they went right over my head. But at a certain point, I realized that what he was doing involved mathematics very similar to what I was doing, or at least where I'd come from. He was depending or groping, in some cases, for mathematics which had been done 30 or 40 years earlier. And that was, at that point, I realized, hey, you know, we're using different words to say some of the same things and so on and so forth. So I got interested in, to some extent, in sort of interpreting some of these things to Frank and his colleagues. And he also told me about an extraordinary experiment called the Bohm-Aharonov experiment, which that would only take me 3 minutes to describe.
Oh.
Well, it's basically an experiment where you expect nothing to happen. Intuitively, you would expect nothing to happen, and in fact, something happens. A coherent beam of electrons, you know, all with the frequencies lined up, you know, coherent light like laser and so, is sent around a circle by reflecting it and comes back and meets itself. In the presence of a magnetic field, you would expect that there'd be a twist, but the coherence would be shifted as a result of this magnetic field, let's say, that they're going through. But it turns out that these fellows, Bohm and Aharonov, did an experiment where there was no magnetic field present that the electrons could detect. It was confined, let's say, to a region way away from where the electrons were. So that the electrons, if they had a brain, would not feel anything. They would just march around very happily and come back and find